Hi, this is Dr. Remenacker. I am going to create a series of videos, um, hopefully each I'm not more than about 15 minutes long, but each I'm looking at an optimization problem in a different application. Now, it is not possible to create every video for every type of problem that you might encounter anywhere in your career over the next 40 or 45 years, because you just can't predict what's going to happen. But what I want to do through this series of videos is to present you with some examples and teach you some strategies for developing solutions. There's a series of general steps to keep in mind when you're solving an optimization problem. The first thing to remember is that the word optimization means make it the best you can. In some situations, that means make it large. In other situations, it means make it as small as you can. For example, if you're trying to develop a computer chip, the objective isn't to make something that's 40 feet long and 30 feet wide. The objective in that situation is to produce something that has the smallest dimensions possible. Okay, so remember that optimization doesn't always mean bigger is better. In fact, if you're trying to optimize your expenses for a business, optimizing your expenses doesn't mean make your expenses as big as possible. What it means is to make them as small as possible. You will need to, in each situation, determine if you're looking to maximize or minimize, and you may even want to jot that down before you start writing out the problem. This is a maximize problem. This is a minimize problem. The first step in the process is actually the most difficult. The most challenging portion is to understand the problem. Okay, so that's why it says to read it carefully. And then what is really going to test you is the development of a math model that fits the situation. The idea is to take something in the physical realm and turn it into an equation that describes what's happening in that physical realm. This can get tricky, okay? This is very likely where you will find the greatest challenge in these problems. And one of the things that's extremely important to do is as you develop your equation, clearly write down a note to yourself. What does the variable even represent? It's very easy to get into one of these problems, maybe 10 minutes into it, and yes, I did say 10 minutes. These problems can take 10 or 15 minutes apiece to solve. Okay, to get into it and then, oh rats, I forgot what does X mean in this situation. Once you have your equation, the series of steps that follow are pretty much routine. As we've talked about many times before, when you're trying to find a maximum or a minimum, the maximum or the minimum will occur at a situation where the slope of the tangent line is zero. We want to locate situations where the slope is zero. This is why we're going to compute the derivative, because the derivative is the slope. And then this is why we're going to take that derivative and set it equal to zero, because we want to know where on the function will the slope equal zero. It's important to be mindful of the fact that sometimes, okay, you can also get situations that'll turn up with a derivative where it's undefined, where the slope is vertical. We've always looked for critical values at locations where the slope is zero, where the um, derivative is undefined. Okay, so we're going to set the derivative equal to zero. Be sure that the values you obtain make sense in the situation. This is really important. Mathematically, we will sometimes come up with negative values. Now, the problem with a negative value is, suppose you want to know how many pounds of some catalyst you need in a chemical reaction. Well, if you come up with a -2, you cannot measure out a -2 pounds of the catalyst. So make sure that the values that you're actually going to use and consider make sense. Mathematically, they make sense. However, in the applied situation, they don't always make sense. Okay, so you've obtained your various values by setting the derivative equal to 0. Then what you want to do is you want to use either the first or the second derivative test. It's your choice. Either of them will work to confirm or identify the values that are either a max or a min. Remember earlier in step 1, you should have written down somewhere that the objective here is to maximize or to minimize. And then apply the first or second derivative test. And we've talked about in earlier situations, sometimes it's easier to do the first derivative, sometimes it's easier to do the second derivative. Either will work. Go with the way that is easier because you're less likely to make a mistake. Once you've identified the maxes or the mins that are appropriate for your situation, there may be several of them. You're going to want to choose the absolute max or min, which is what we have looked at in a previous video, finding the absolute max or min as opposed to the relative. If you have two different options for production, one will produce a profit of $50,000 a week and the other will produce a profit of $230,000 a week, I think it's pretty obvious that the second option is going to be the more desirable one. So be careful not to just pick a relative maximum or a relative minimum, but to choose the absolute maximum or the absolute minimum. Last thing, and this is really important. You've seen this in several earlier videos. Once you have an answer, you don't want to just walk up to your client and say 17. Say what? Yeah, 17 is the answer. The answer to what? 17 what? What am I supposed to do with that? What you're going to want to get into the habit of doing, and this is going to be very important as you move into your career, is become accustomed to giving an answer that identifies the question that was asked as well as other values or information that are related to the problem but maybe weren't the first question. For example, you might be asked, well, how many cans do we need to produce a day to maximize profit? Okay, so you can come up and you can say, well, we need to make 30,000 cans a day. Do you think the supervisor or the owner of the company is just going to say, great, 30,000, let's start? Well, they may have some other questions like, how much is this going to cost? What's the profit going to be? How much material do we need? Okay, how much labor do we need? So there are other questions that factor into achieving this profit of $30,000 a day or whatever it is. And you want to be able to have all of the answers in one concise location instead of them having to play 20 questions with you trying to draw out from you everything that's really needed to implement the answer of make 30,000 cans a day. Okay. These questions often have a variety of um, information required to implement it. Okay, so with these 6 steps in mind, let's take a look at a first situation. On each video, I will take a look at a different type of problem. I'm trying to keep these videos a little bit shorter so that there's something that you can bite off and digest at one time. Okay, classic example. You have a sheet of cardboard that is 10 by 12 inches long. One of the ways that boxes are formed is by cutting a tab from each corner and folding the sides up. On the right side here, you can see where a tab has been cut from each corner. All 4 corners are missing a tab. Several things to notice. Okay. First off, the tabs need to be square. I guess I need to have an A in there. Spelling counts. Okay. If we were to cut a tab that went like this, when we fold this side and this side up, they won't be the same height. And you'll have a box with two of the sides taller than the other two sides. And that's not desirable. So one of the first things that we need to notice here is that the tabs must be square. Notice I haven't read the whole thing. I've just read the first sentence here. What size tab must be cut from each corner to maximize the volume? Here's what we want to do. Our objective is to maximize the volume. What size tabs have to be cut to maximize the volume of the resulting box? Well, one of the first things I want to do here is to remind myself that volume is the equation length times width times height. I know that these tabs that are going to be cut out have to be the same size on each side. They have to be squares. And the question is, how big of a cut do we make? That's what we really want to know is if we're looking at one side here or the other side, how long or how big does that cut need to be? Because they're square, the cut on each side has to be the same length. So what I'm going to wind up doing here is I will define each cut side as x. Okay, and I'm going to leave my x in that picture so that I have an idea of what's going on. The next thing I want to do is I want to consider the overall dimensions of the starting piece of paper. It starts out 12 inches long and 10 inches wide. Okay, so I'm getting some information down. What I want to be able to do is to figure out the volume of the resulting box. Notice it's not going to be a length of 12 and a width of 10. Because if I use the length of 12 and the width of 10, how tall is it? Well, we haven't folded anything up and our height is 0, so the volume's going to be, 0. So we're going to have to figure out some way to describe what the length of the box is going to be once we have it folded. Okay, so the length of the box, looking at the bottom picture here, is going to be this amount, L. The width of the box is going to be this amount, W, and the height of the box is going to be this amount, H. We need to figure out a way to describe each of these three measurements using just that one variable x. Well, let's take a look at what's going on. I'm going to look at the top of the two pictures. When I fold the box up, I'm looking at this bottom tab. I'm going to fold it along this line. Then on the sides, I'm going to fold along this line and this line. And then on the top, I'm going to fold along this line and fold those 4 tabs up. When I'm finished doing all of the folding, the bottom, the base of the box, is going to be this area that I'm shading in right now. The length of that box, the shaded in area, okay, and that shaded in area is this length right here. The length of it, which matches this measurement here, is going to be the whole 12 inches, because remember I started from there to there. It's going to be that whole 12 inches, but I've cut away this much on the left side, X, and this much, same amount on the right side, X. So the length is going to be the 12 inches that I started with minus an X minus an X. In other words, take away the length from each side, which is going to give us a length of 12 minus 2X. The width is going to work the same way. Okay, the only difference is for width, I'm drawing back on the top box, the width is this amount. The width is going to be the whole width of the box minus this amount at the top minus that amount at the bottom. So the width is going to wind up being the 10 minus the 2x results from cutting out the tab. The third thing we need to do is we need to look at the height. Well, the height is just one of the sides folded up. And when you fold one of these sides up, okay, looking at the bottom tab on the top box, when you fold one of the sides up, this blue arrow here is going to be the height of the box. The height of the box is just whatever the x value is because that's how far in you've cut to create the tab. All right, so I can now write my volume. My volume is going to be the length, 12 minus 2x, the width, 10 minus 2x, and the height, x. I could take the derivative of this using an extended product rule. Yeah, that looks like a lot of fun. And remember, once I get the derivative, I'm going to have to set it equal to 0. So algebraically, I want to clean this up as much as possible so that it's an easy equation to solve, set equal to 0. Well, to accomplish that, what I'm first going to do here is I'm going to multiply these two together, which is going to give me the 12 times 10 is 120. The 12 times the minus 2x is minus 24x. Then we have the minus 2x times the 10, which is minus 20x. Then we have a minus 2x times a minus 2x, which is going to be plus 4x squared. Now be careful because we're not done. We still need to multiply everything by x. Okay, well, before I go ahead and multiply everything by x, I'm going to take what's in the first set of parentheses and clean that up a little bit. I have a 4x squared minus 44x plus 120, and that's going to be multiplied by x, which is going to give us a volume formula of 4x cubed minus 44x squared plus 120x. Now be careful. We don't set this equal to 0. We don't. Now if you come up here, step 2 says compute the derivative. So I'm up at the very top of the screen. Compute the derivative. Then step 3 is set the derivative equal to 0. Oh, that's right. So the next thing we need to do here is we're going to compute the derivative. The derivative of this function is actually pretty easy. It's 12x squared minus 88x plus 120. There's the derivative. That's step 2. Step 3 says to set it equal to 0. At this point, you can do one of two things. You can try to solve this by hand, or I'm just going to go on my calculator, pull up the quadratic formula that you should have programmed into yours. A is a value of 12, B is negative 88, and C is 120. This gives me two values for x. X can equal 5.523, or x can equal 1.811. All right, so I have x values, but what do these x values mean? I'm going to return to the picture over on the upper right-hand corner. These x values are a length of tab that we're going to cut out. If they're a length of tab, that means these are going to be measured in inches. Now, we have two options. Both of them mathematically are absolutely fine. However, mathematically, one of them won't work. Take a moment and figure out why one of these won't work. Well, if you'll notice, the width is only 10 inches on the starting piece of cardboard stock. If we cut out a tab that's 5.5 inches, That's a problem. Okay, what's going to wind up happening is, and I'm going to erase some of this, coming down from the top, okay, if I go and I cut a tab that's 5.5 inches, it'll work fine there, but it's going to come down 5.5 inches. Okay. Then when I go to cut a tab from the bottom, I'm going to come up, but measuring 5.5 inches is going to take me beyond the first tab. You cannot cut that wide of a tab out. You only have 10 inches of material. You can't cut 11 inches off of a 10-inch piece of paper. So what's going to wind up happening is this first option here really isn't going to work for us. We're just going to say, nah, that's not it. What we want to do now is we want to consider our value x equal to 1.811 inches, which says each side of the tab is 1.811 inches, almost 2 inches. Before we go any further with building the box, let's check and see what our steps are. Okay. Step 4, now at the top of the screen. Oh yeah, we got to use the first or the second derivative test to verify that the value that we have is a maximum or a minimum. Remember, in this case, we are trying to maximize the volume. So what I want to do is I want to take my x equals 1.811 and using either the first or the second derivative, determine if this is a max or a min. If I was to use the first derivative test, what I would wind up doing, and I'm thinking this out just to show you what's going on. I have something like 1.811 and 5.523. I realize we're not going to use that second one, but I want to make sure that when I pick a value, it's not beyond the second point. I could evaluate like this. Now it's going to require me to evaluate twice, okay? So it might just be the quickest way to do this is to put in a 12x squared minus 88x plus 120. Go to the table on my calculator. I know I'm not showing you the calculator at this point. I'm assuming you're good to go with that. I'm going to put in 1. I'm going to put in 2. 1 winds up being greater than 0. 2 winds up being less than 0. Okay, so greater than 0 means the slope's positive. It's increasing. Less than 0 means the slope is negative. It is decreasing. If we go from increasing to decreasing, this is a max. So one way to verify this is using the first derivative test. I'm going to use both ways just so that you can see how this would work out either way. If I use the second derivative test, I need to compute the second derivative. In this case, the second derivative, you can look at that and you can write that down. Remember way back at the start of this course, most of you were not able to look at something like that and just jot down what the derivative is. Now what we're going to do here is we're going to evaluate this derivative at this 1.811, and that's not hard to plug into your calculator. Okay. In fact, I'm not even going to bother plugging it into my calculator because it doesn't have to be perfect. If I take this 1.8 and multiply it by 24, well, that's kind of a little smaller than 48. Yeah, well, we need to be more exact than that, don't we? Not really, because we're subtracting 88. And if I'm around 40, 50, something like that, regardless what I do, this is going to be less than 0. Now, if it's less than 0, that means concave down, which means that our point is going to be a maximum. So using either the first or the second derivative test, either way, I can verify that this is a maximum. All right, so where do we go from here? We've confirmed that we truly do have a maximum. That was step 5. Step 6 is to summarize what you have. What have we figured out here? Well, we still haven't figured out the dimensions. So I'm going to need to jot down the dimensions. Before figuring out the dimensions, we want to make sure that the value we're going to be using works. There's no sense putting a bunch of work into something that isn't worth messing with. The length was 12 minus 2 times 1.811. The width was this 10 minus 2 times 1.811. The height is just the 1.811. And remember, these dimensions are going to be in inches. Now, I'm going past just answering the basic question. Notice at the very top of the screen, the question is, what size tab must be cut from each corner to maximize the volume? Well, you could go back to your supervisor and say, well, cut a tab that's 1.811 inches and walk off. That's probably going to leave them with a few questions in mind. Like, well, how big is this box going to be and how much can it hold? Well, yeah, I guess those are legit questions. So what we're going to do down here is, in addition to determining the size of the tab that we need, 1.811 inches, I'm going to do this 12 minus 2 times 1.811 equals, this means the box is going to have a length of 8.378 inches. The width is going to be 10 minus 2 times the 1.811, which is going to give us then a length of 6.378 inches. The height, that's already done. So now we have the dimensions. One other question that we can answer here is, okay, so what's the volume of the box going to be? How much can it hold? Okay, I'm just trying to think ahead to the questions they might ask. In order to do that, I take the length, 8.378, times the width, 6.378, times the height, 1.811, equals, the volume winds up being 96.771 inches cubed. Be careful, we're talking about volume here, not length. All right, so we now have some information. And at this point, we have enough information that you could come back to your supervisor or your client and give them an intelligent answer. Okay, the solution is to maximize the volume, cut tabs, square tabs, that are 1.811 inches on a side, period. This will produce a box that is, oh, we need to get these numbers here, 8.378 inches long, 6.378 inches wide, and 1.811 inches tall. The volume of the box will be 97.771 inches cubed. Okay, to get cubic inches there, I have to use that symbol. Okay, I'll fix my spelling on produce. Now, realistically, if you think about this answer that's written out here, I know it takes a little more work, but when you come back to either your supervisor or your client, if they've hired you to figure this out, you want to be able to say more than just 1.811, and I think you can see that an answer like this really works. And actually, I need to fix the volume on the box. It should be 96. There. I wasn't hired for my typing. Okay, 96.771 cubic inches. This is the first of a number of different problem types we're going to be doing. I hope this is useful.